electronic devices. Here, so good morning all. Just we are going to have we are going to discuss today Unit 3 Optoelectronics. So what does mean by optoelectronics? It is nothing but the study and application of electronic devices that source, detect and controls light. In the sense, optoelectronics is the communication between optics and electronics, which includes study, design and manufacture of hardware devices. Hardware devices means like LED, solar cell, etc. Those devices which converts electrical energy into light energy and light energy through semiconductors, because all these whatever the devices we are using are semiconductor devices. So optoelectronic devices are basically electronic devices which involves light. Clear? So we have so many examples of optoelectronic devices which includes telecommunication laser, optical fiber, LED traffic lights, photodiodes, solar cells, etc. Clear? So we are going to discuss 5 devices in this optoelectronics. So before going to the devices, we'll have the concept over here. What is the basic concept which we are using over here? It is a recombination, that is recombination of radiative and non-radiative. In the sense, radiative recombination and non-radiative recombination. What does mean by this recombination? Whenever an electron and holes combine to form an electron-hole pair, they call it as recombination. Then what is this radiative recombination? Whenever an electron in the conduction band recombines with holes in the valency band and excess energy is emitted in terms of photon, light, that is called as radiative recombination. Instead of that, if energy, that is in terms of heat, is released, then we call it as non-radiative recombination. So whatever the devices we are going to discuss in this unit are working on this principle of radiative and non-radiative recombinations. Okay, so I have given you in theory, that is in PDF, a differentiation between radiative and non-radiative recombinations. That is a table I have given in the PDF. Please go through it, because this is the only small question in this unit. Only one question is there. So definitely it will be associated with any other question. So please go through these definitions. Got it? So only 5 points I have given. First one is the definition of this radiative and non-radiative. And then I have given the diagrams, okay, geometrical diagrams of this. And what is the probability of radiative recombination? It is very high compared to non-radiative. Okay. And similarly, what is the efficiency factors and examples of this I have given in a tabular column, which I have posted in the PDF. Please go through that. Okay. Now coming to the devices. What are the some optoelectronic devices? We have photodiodes, photodetectors, photovoltaic devices, and lasers. So in lasers, we can discuss diode laser. Okay. So out of that, the first optoelectronic device which we are going to discuss today is the LED. LED already experiment you did in your physics lab, isn't it? LED VI characteristics and PI characteristics already we did, and you know how the device is working and what is the circuit diagram. Practically, you have come across the light emitting diode. So even though just we'll have a gist of this. Okay. So it is an optical diode which emits light when forward biased. Remember, if you are perfect with the concepts of this LED, you can do very well in theory as well as in practicals, because we are having lab external exams also after this, after your midterms are anyway in this month or next month. Clear? So if you are perfect with these concepts, it is very easy, you people, for answer this Viva questions. Okay, so LED is an optical diode which emits light when forward biased. So it is similar to PN junction. What is the symbol of PN LED? LED is nothing but simple. It is a the symbol is like PN junction, but only thing is we are having 2 arrows extra. What are these 2 arrows are explaining? They are indicating that device is emitting light. Okay, now this is the symbol, general symbol and this is a general structure of a light emitting diode. So what is LED? It is an acronym of light emitting diode. Okay, so it is nothing but a PN junction diode which is connected in forward bias mode. Now coming to the construction of an LED. What is the basic operation and what is the construction? See here, in LED, what are we doing is simply we are using to, for the construction, we are depositing P-type and N-type layers on a substrate. Okay, substrate is nothing but first we are taking N-type layer, then we are taking a P-type layer. Okay, just we are sandwiching them. And above that we have 2 ohmic contacts. And the active region is nothing but junction. So the PN, that junction between P and N emits light whenever electron and hole recombination is taking place in the forward bias condition. So holes from the P type and electrons from the N type both are getting driven into this active region. As a result, they recombines and light is emitted. So in this particular structure, we are having some different thing, isn't it? Here we are placing an LED, so which is in the form of a strip. So there we can say it is a structured layer, okay, in the form of a substrate. But here what we are doing is, whenever light is emitted, it is emitted in all directions, in all 4 directions. Then what happens? It is radiated. That means its intensity will be low. In order to have the high intensity, always in particular structure, LED is way around a layered structure. So what we are doing is we are placing this in a tiny reflecting cup. You can see this is a simple cup, a small cup. We are placing the LED in this cup and it is encapsulated by a layer, that is a plastic encapsulation, so that it is, that is whatever the light is emitting, it is exhibited in a desired direction. That is, it is oriented in a one single direction so that its intensity will be high. So therefore, a plastic case is enclosed and the chip area of the LED frame, so that it is, that means there is a small opening or a transparent thin film is attached so that light is emitted only in that particular direction. Already you people have come across how the light is emitting out from a small simple box in a LED circuit. Already you have seen it. Now coming to the working part. Now already we discussed that P-type and N-type layers are sandwiched. That means we very well know that free electrons are present in the conduction band and holes are present in the valency band. So we know very well that free electrons are at higher energy level compared to the holes. So when a free electron is combined with a hole, it falls from conduction band to the valency band. So then what is happening? The energy level associated with it changes from higher value to the lower value. So the corresponding difference in the energy is released in the terms of light and it is denoted by Eg, that is equals to h mu. So here light is emitted, that is why we write mu in terms of C by lambda. So then what is the energy difference over here? Eg is equals to hc by lambda. Whereas this is the case with LED. In normal diodes, energy is released in terms of heat, like PN junction diode. In terms of PN junction diode, it is released in terms of heat. That is the difference only. That is why we are indicating 2 arrows in the case of LED. So why it is light is emitted only in LED? Because LED is made up of some special materials. That is, apart from P and N, like germanium and silicon, we are adding gallium, aluminum, arsenide, phosphorus, indium, like that. Okay, but in general, the major LEDs for the different applications are always made up of gallium arsenide, gallium arsenide phosphide, gallium phosphide, etc. Depending upon the base and concentration of doping of all these materials, the output color will be varied. different materials, different colors. Like, for example, gallium arsenic phosphide always emits red or yellow color. While gallium phosphide only gallium phosphide emits only the red or green light. Okay, and remaining some other gallium aluminum arsenide like that, they will emit blue and orange light. So like that, depending upon the concentration of doping of all these different materials to this germanium and silicon, varies the energy differences and frequency differences, so that the output color also varies. Okay, so this is what already we have discussed in the lab also. Okay, so whenever current flows across a diode, negative electrons move one way and positive holes move the other way. So the holes existed, already we discussed this, lower energy level than free. So the difference in this is coming out in terms of light. So these are the different structures and shapes of LEDs depending upon the application which we are using. Okay. So actual color always depends upon the material which we are using. See here, the different applications, see different dimensions they will be, and they will be traditional, multicolor, bicolor, tricolor, like that. Okay. So now coming to the VI characteristics. This already the same circuit diagram we have used in lab also. Clear? So LED works only with forward biased condition. It may work, it might work with this reverse bias also, but output is very, very low. That is why we will never use LED in terms of reverse bias. So always we use it in the forward biased condition. Clear? So these arrows are indicating that light is emitted out. So what are we doing initially? So first we will change the voltage so that for particular voltages like 0.7 to 1.1, there is no change. And after 1.1 electron volts, slowly the light starts, that is diode starts glowing and current starts flowing, very, very minute current. But in our laboratory, we observed that after 1.5 electron volts only, the diode starts conducting and current is flowing. So that is why from origin to this place, there is no conduction in the diode is taking place. So we call this area as non-operating region. And after a particular voltage like 1.5, after 1.5 or 1.6, diode starts conducting and exponentially the current increases. Clear? So therefore, at what voltage the diode starts conducting is known as threshold voltage or cut-in voltage. Clear now? So then afterwards, linearly it is increasing. Your graph is linearly increasing. So you have to identify from the graph what is the threshold voltage. Okay. So the resistor here, whatever we are using the resistor, it is a current limiting resistor. Due to this resistor, current through the circuit is limited and prevented from exceeding the maximum current rating of the diode. If not, the diode will get damaged. That is why RS, that is current limiting resistor, is connected in series with this. So you can apply the Ohm's law and you can calculate what is the source voltage. So in forward biased condition, voltage drop across the LED is minimum 2 to 3 volts, which is considerably greater than across a normal silicon and germanium diode. The amount of power output translated into light. So whatever the current is coming out, it is generated in terms of light. That is, it is directly proportional to the forward current. Clear now? The amount of light intensity which we are getting, it is always proportional to the forward current. That is why we are doing PI characters also in lab. That is the luminescence as well as the luminosity versus current plot also we are plotting in graph in laboratory. Okay, so that is why we say the LED. What is the basic principle of LED? Generally we say it is a electroluminescence. Why? Because whatever the energy is released, it is released in terms of light, and that principle is known as electroluminescence. So in lab external, if they ask what is the basic principle of LED, we should say it is the electroluminescence, and we are doing. If you want, here also you can mention the graph, it will be reverse. It is in this direction. Okay, P and I characteristics. We are calculating if current is increasing, luminosity is also increasing. Clear now? So these are the VI characteristics of LED. See here, for different colors, we have different for different concentration of materials, different colors will be there, and what will be the brightness, just I have mentioned. Okay, so this is the now coming to the applications of merit. So I mentioned one more thing over here. In this unit, they will ask you, instead of application, sometimes mention figure of merit, figure of merit of the optoelectronic device LED. What does mean by figure of merit? Figure of merit is also nothing but the applications only. That is, it is nothing but it explains you the performance of a device. Figure of merit is nothing but performance of a device, system or method. It explains you about the target performance. Clear now? So how much that means it is efficiency. Target performance is nothing but efficiency. And where can we apply this? So don't get confused with that question. Explain the figure of merit in the sense it is nothing but advantages or applications of LED only. So basically we know very well that all display devices are nothing but LED because they are very small in size and they are regarded as a point source of light. Because of that, it is used as a display device. That is in your digital watches, in your calculators, majorly it is used as a 7-segment display. Okay, and its brightness is very high, isn't it? That is why, because of that, it is used for ambient lighting conditions, that is in decorative lights, and in solid state lighting, in communication, because they are light in weight and have long life. So therefore, household supply domestic bulbs are also nowadays replaced by LEDs only, and they are very fast operating devices. Because of that, they are interfacing with various other electronic circuits. Clear? And all remote control and communications in all these fields, they are used. These are all applications of LED. Got it? And I have given a tabular column, the differences between LED and PN junction diode also. Sometimes instead of the short answer question, what are radiative and non-radiative recombinations, they may also ask distinguish between LED and PN junction diode. Okay, in that case, you should be in a position to write the differences. So I have mentioned some 8 differences between LED and PN junction diode. Just you can go through it. So this is also be considered as a small short answer question. So the first short answer is radiative and non-radiative recombinations. If not, they may also ask you this LED or PN junction diode. Got it now? Now coming to the next part of this unit, that is photodiodes. What are photodiodes? In generally, a diode obtained by sandwiching, that means it is nothing but which emits. Photodiodes is nothing but a PN junction. Basically, they work under reverse bias only. Now, whatever the devices we are going to discuss now, they are working under reverse bias. So they are also semiconductor devices which are made up of P and N, but specifically the doping concentrations and intrinsic region is included in these photodiodes. Okay, they may work under the principle of the photovoltaic or conductive mode. That is why these are called as the photodiodes. Got it now? Now under this first device, see here. The first we are discussing about a solar cell. Okay. So what is a solar cell? It is also known as a photovoltaic cell. So it is basically a PN junction that generates electrical power when illuminated. So these are usually a large area devices and typically illuminated with sunlight and are intended to convert solar energy into electrical energy. But all the time, sunlight is not available, isn't it? And it may not be possible to use sunlight always for these devices. That is why we are using some artificial devices, okay, which we call it as the photoconductor solar cell. Okay, it consists that is, and these are also known as those artificial cells which we are using. That is DC cells, photovoltaic cell. Okay, so the term solar cell is designated to capture energy from sunlight, whereas PV cell, that is photovoltaic cell, is referred to as unspecified light. In the sense, here we are not using exactly the sunlight. That is why we always in laboratory conditions will be using photovoltaic cells. Okay, it is like a battery because it is supplying a DC power. Okay, so now coming to the principle of solar cell. Okay, so solar cells are basically working on the principle of photovoltaic effect. It is nothing but generation of charge carriers in light absorbing materials a result of absorption of light radiation. Clear now? This is a general solar panel. It is a general solar panel. If electrically, if we connect P and N type, only one single P and N, then we call it as a single solar cell. Like this, if we are taking a cascade of PN junctions, then we call it as a solar panel. Clear? So how many types of solar cells are existing? There are so many. That is monocrystalline, polycrystalline, and amorphous. Okay. So monocrystalline, mono, the word is explaining you that it is a single. It is produced from the pure silicon. Okay. And polycrystalline means we can use different like liquid silicons or we can say a combination of different crystals. Okay. For this purpose of and other one is like a substrate or glass plate. We are using the amorphous silicon. Okay. So generally in practical, in all these applications, practical applications will be using the substrate or glass plate, that is nothing but amorphous silicon. Okay. So the dimensions of this is also mentioned over here. Okay. Now construction. Coming to the construction of solar cell. So how do we construct solar cell? So here in this, a crystalline silicon which consists of N-type semiconductor and a P-type semiconductor, that is a layers. Two layers are sandwiched. Hence, there is a formation of PN junction. So we know that very well, isn't it? So what are we doing is, in the construction part, here this PN junction is constructed by using different semiconductor materials. But in generally, we use germanium, silicon, or gallium arsenide, or indium arsenide, or cadmium arsenide, etc. For the construction of solar cell, we are using such type of materials. Okay, this is the construction. See, you can see over here. Okay, so the PN junction is packed in a cylindrical metal which consists of a glass window on top. See here on top and bottom will have a glass window, and we are using ohmic contacts on the top and bottom. That ohmic contacts in the top can be coated with a nickel plate. Okay, it is in terms of some metal rings or metal rods on the top. That is a P-type is acting like a positive, positively doped, and it is acting like a positively output terminal. Whereas at the bottom side, that metal contact is acting like a negative output. Clear now? So P and N junctions are taken, and they can be made of germanium silicon, gallium arsenide, indium arsenide, cadmium arsenide, etc. And above this and below this, we are coating with a metal. So at the top, we are taking a nickel coating in terms of either metal rings or metal. See here, you can see metal rods in terms of metal rods like a panel-like structure. And at the bottom, it is serving like a negative output. So in order to avoid the recombination of generated electrons and holes in P and N regions, their thickness is kept very small. They are very thin. For the generation of more number of charge carriers under the influence of the incident light, because either sunlight or any other light, source light which we are taking, what we are doing is heavily doped P and N type materials are used. Clear now? We are taking P and N which are very heavily doped. This is all about your construction. Now coming to the working part. When the photons of suitable energy, so either sunlight or any other light is allowed to incident on this PN junction. Now what is happening? Photons are gaining sufficient energy to the valency electrons, and they are removed from their parent atoms. So then what is happening? Electron hole pairs are generated in both P and N region of the junction. So these newly generated charge carriers are reaching the depletion region by diffusion, where they are separated by a strong potential barrier. Okay. So at the same time, minority charge carriers are supported by the existing potential barrier at the junction for their flow across the junction. Clear now? So therefore, flow of minority charge carriers across the junction constitute the minority current which is directly proportional to the illuminated, and also it depends upon the surface area. See here. So now coming to the next part, characteristics. And also I hope you remember the circuit what we have designed in the lab. We did this experiment solar cell in applied physics lab. So we had a PCB over there. Directly, we are taking a lamp and just we are connecting, isn't it? We are connecting in the reverse here. See here, you can see. So this is the negative electrode and this is the positive electrode. We are connecting it in a reverse bias. Okay. So what are we doing here? What can we observe in this graph, in this plot? We are observing open circuit voltage, short circuit current, maximum current and maximum voltage. Clear no? Maximum current and maximum voltage, and also MPP, maximum power output. So in this experiment, what are we doing is we are changing the resistance over there. Okay, for different resistances, current is varied. Clear? Then we are plotting the graph. And from the graph, we are calculating, we are obtaining, or we are explaining 5 parameters. One is short circuit current, open circuit voltage, and maximum current, maximum voltage, and what is the maximum power output. If you know what is the maximum power output, then you can calculate what is the fill factor and what is the efficiency of this solar cell. Got it now? So how to calculate it now? See here. First, initially we discussed what is the open circuit voltage. So what is that open circuit voltage? It is VOC. The voltage across the illuminated cell at zero current is known as open circuit voltage. Then what is short circuit current? This is a short circuit current. Here, this is short circuit current and this is the open circuit current. So what is the short circuit current? It is a maximum current from a solar cell when voltage across the device is zero. When voltage is zero, then we get a short circuit current. Got it now? So then if you draw a line from this bend, from exactly where the current is decreasing, that point you have to identify, and from that graph, you have to draw a line like this, line to the y-axis and draw a line to the x-axis. Then you can identify on the x and y coordinates what is the maximum current and what is the maximum voltage. So then if you multiply what is the that is maximum current into the maximum voltage, then you can get the maximum power output. Then what is the fill factor? Fill factor of a solar cell is defined by, it is nothing but maximum power output by short circuit current. It is the ratio of maximum power output by short circuit current. Similarly, efficiency. Efficiency is nothing but war and how best we can use this solar cell and where we can use this solar cell can be explained by a factor known as efficiency. It is always denoted by neta. Okay, so that is efficiency. Theta is equals to ISC, that is short circuit current, multiplied by the open circuit voltage divided by the input voltage. Okay, sorry, input power into the fill factor. This gives you the efficiency. Got it now? So these are the factors which we have to identify and obtain, and you have to remember from the solar cell. So whenever you are writing the VI characteristics of solar cell, what all you need to write? You have to explain about the, first you explain about the working condition of a circuit, okay, that is the device, and then draw this diagram, explain first what is short circuit, then explain about open circuit voltage, and explain the definition from this formula. Write down the definition. It is the ratio of maximum power output to the short circuit current. Okay, and write the definition of efficiency. Okay, all these 5 definitions should be there in your answer. Then only it is considered as the VI characteristics of solar cell answer is completed. If not, it is incomplete. Got it now? Based on all these, what are the applications? I told you again, I repeat it. Applications are nothing but figure of merit. So whenever figure of merit is asked, you have to write either advantages or applications only. So what are the applications of solar cell? It is nothing but it is majorly used in domestic power supply, okay, and electric power generation, in space, that is in satellite communications and all. So because they have been remain a best choice for providing electric power used in operations of satellites and space vehicles. That is why it is used in this satellite communications. And it is also used for domestic power supply in remote villages, and few houses in domestic appliances in applications in even city also they are using, okay, like solar panels instead of that is in inverters. And they are frequently used in the electrification of healthcare facilities and in farming like irrigation and water supply, and also in many lighthouses and bios in navigation, okay, and water heaters generating electrical power, okay. So like this, for various applications, solar cells are used. So remember, in all these diodes, how to explain about a diode? First, you have to explain what is it, what is the basic principle, then coming to the construction, then go for the working, and then go for the VI characteristics and applications or advantages are the figure of merit. Clear now? I repeat, for all these answers in Unit 3, Optoelectronics, we have 5 basic devices. For all these devices, you need to write answer in the same mode. First, introduction. Second one is basic principle. Third one is construction. Next, go for the working. And next, go for the VI characteristics. And the last one is applications or figure of merit of those devices. So please remember these headings, side headings. The remaining things automatically you can write. Okay, so we have completed solar cell. Now coming to the diodes, photodiodes. We have two types of photodiodes. First one is pin photodiode and the next one is avalanche photodiode. So in pin photodiode, so here you can write it as pin photodiode. It is not pin diode, it is a pin photodiode. Okay. So this is the symbol of pin photodiode. Okay. It is a symbol of pin photodiode. In generally, the diode circuit symbol will be like this. And coming to the structure part, it will be like this. So in general, we can say a diode which is sandwiched between a pure intrinsic semiconductor between a p-type and n-type is known as pin diode. P is a p-type, I is the intrinsic, n is the n-type. So intrinsic I is sandwiched between p-type and n-type diodes. That is why this diode is called as pin photodiode. Got it now? So it consists, then these two P and N type are heavily doped. So remember, in this diagram, plus is added to P and N. You can observe plus. So whenever P plus and N plus is mentioned, it is nothing but they are heavily doped. Clear now? So in between this P type and N type, an intrinsic region is introduced between them. So the symbol is almost similar to the conventional PN junction diode. Now, what is the working principle of PN junction diode? See here, this is the construction, P-type and N-type, and intrinsic region is over there. So, the working principle, that means PN diode, PIN diode behaves differently in forward biased and reverse biased condition. It works with both forward and reverse bias. Now, coming to the forward biased mode. In forward bias, holes from P side and electrons from N side. Just go through the circuit here. Okay, this is the diagram. You can go through it. So holes from the P side and electrons from the N side are injected into the I region. I is nothing but intrinsic region. So what is happening is this is increasing the carrier concentration. This is increasing carrier concentration in the I region. So then what happens? It decreases the resistivity and increases the conductivity modulation in PIN diode. So this forward current flows due to both electrons and holes. So therefore, in forward biased condition, PIN diode acts like a current controlled variable resistance. Current controlled because resistivity is decreasing over here and conductivity is increased. That is why it is acts like a current controlled variable resistance. So please remember such points for objective point of view. Okay, so what are the materials which are used and what is the symbol? Okay, and how many types of junctions are there in this? What is the materials with which it is prepared? Okay, and what is the basic application of these devices? On all these factors, on all these parameters only, objective questions you can expect. Got it now? So therefore, in forward bias mode, it is used as current controlled variable resistance. Now coming to the reverse bias. In reverse bias, see here, in the reverse bias, you can see. In reverse bias, holes and electrons are moving in the opposite direction. See here, they are moving in the opposite direction. You can go through the diagram. So what is happening, and I region, that is intrinsic region, will become free from these charge carriers because they are moving in the opposite direction. So this depletion region is swept free region. It is also called as swept free region in the sense there are no charge carriers. So the length of this depletion region will be increased because more the voltage which we are applying over here, more the charge carriers are attracted towards the applied voltage. So the length of the depletion region is always almost equal to the length of the in the intrinsic region. So what is happening? It is acting like a transition capacitance, like it is acting like a parallel plate capacitor over here. So it is acting like a dielectric in this case. That is why we can say in the reverse biased condition, pin diode is acting like a constant capacitance or transition capacitance. It is acting like a transition capacitance, which is denoted by CT. Clear? Now coming to the characteristics. So you can plot a graph forward current versus the series resistance. On x-axis, you can take forward current, and y-axis you can take series resistance. Then what is happening? Gradually the current is decreasing. If current resistance is increased, current will be decreased. Okay, and vice versa. That is why it is used as a current controlled device. And coming to the second part, if you plot a graph, reverse voltage versus capacitance, it is acting like a transition capacitance. It is acting like a parallel plate capacitance over there. Okay. So then what are we obtaining from these graphs? We are plotting two graphs in the forward bias and reverse bias. So from these forward and reverse characteristics, what are you obtaining for this pin diode? We are obtaining responsivity. What is responsivity? That means whatever the output which is coming out, how much, what is the intensity of it? What is the responsivity? So primary photocurrent which is resulting from the absorption is always denoted by this equation, Q by H mu, P naught into 1 minus e to the power of alpha s. These are all parameters, saturation parameters into lambda and width of the intrinsic region, and this is the forward resistance. From this, we are calculating the quantum efficiency. Quantum efficiency is nothing but neta. Quantum efficiency is denoted by neta. Neta is equals to number of electrons, ash is nothing but here number. Number of electron minus whole photo generated by pairs. How many number of electron hole pairs are generated over there, divided by the number of incident photons. So if you substitute all these parameters in this formula, you can get the quantum efficiency. And in simple, instead of writing all this, what is the responsivity? Responsivity is nothing but photocurrent by the output voltage, output current, okay, output power. So therefore, responsivity is the ratio between photocurrent by the output power. So it is denoted with neta Q by H mu. Neta Q by H mu. Neta is the efficiency. If you know the efficiency, if you know the number of charge carriers, H is constant, frequency is constant. If you substitute all those parameters over there, you can write responsivity. Or else directly from the plots or directly from the device, if you know what is the photocurrent and if you know what is the output power, directly you can substitute over here and then calculate the responsivity. So for objective point of view, all these formulas are very important, and the formula is like responsivity is obtained from the pin photodiode. Got it now? So this is all about your pin photodiode. So based on this pin photodiode, I have given at last the applications commonly because these are both will come under the category of photodiode. So that is why I gave applications like this. Okay. So based on this various applications of pin diode, they are nothing but they will be used as a DC controlled microwave switch. And they are also used in audio CD players, DVD players, computer CD drives, and optical communication systems. In optical communication systems, in the part of detectors, this pin photodiode and avalanche photodiode will be used. Okay. When you discuss the next unit, optical fibers, there will have optical fiber communication. In that optical fiber communication, hope most of you have did this bending loss experiment also in our applied physics lab. In bending loss experiment in applied physics lab, we have a devices transmitter and receiver. At the part of receiver, we are using these photodiodes in order to detect the electrical light which has been converted from the light. Okay, so we are using optical communication systems, nuclear radiation detectors, like that. So many various applications are there for this pin photodiode. Got it now? So here also, how to write this pin photodiode? What is pin photodiode? Then coming to the basic principle of photodiode, then write down the construction and then write down working principle. So here in the case of working, we are writing both forward and reverse bias, plot the graphs in forward and reverse bias, and then write down the output what you are getting from this graph, then go for the applications or figure of merit of this photodiode. Got it now? Now coming to the second type of photodiode, it is avalanche photodiode. The word avalanche, the avalanche explains you the multiplication. The word avalanche itself explains it is multiplying, multiplication of photocurrent to provide the gate. So these avalanche photodiodes are high sensitivity, high speed semiconductor light sensors. So compared to regular pin diodes, APDs have the internal region where electron multiplication is taking place. Because of that, it is applied for external reverse voltages and result gain in the output signals. That is, in the detection part, mostly these APDs are used. Okay, now coming to the construction part, just go through the circuit diagram. In the circuit diagram of avalanche photodiode, the device is essentially a reverse biased PN junction. And here also N plus and P plus, that is P type and N type are nothing but they are heavily doped. That is, we always should mention it with plus. So P plus and N plus, they are heavily doped. And these are very working at low resistance. And in between, whatever the depletion layer is there, white depletion layer, this is nothing but intrinsic region. And this intrinsic region is lightly doped. Remember, P and N are heavily doped and intrinsic region is lightly doped. So most of the incident light is passed into this, it passes into this intrinsic region through the P type. Remember, incident light, most of the incident light is passes into the intrinsic region through the thin P plus, that is heavily doped P region, and electron hole pairs are generated in the intrinsic region. So under reverse bias, most of the applied voltage drops across the PN junction. So then with the increase in reverse bias, the depletion region across this junction becomes very high and the junction approaches the breakdown condition. So what is this breakdown condition? This is avalanche breakdown mechanism. So in the case of this depletion region, avalanche breakdown is taking place. Due to that, more number of electron holes are generated, which are how they are generating? They are generated by light, incident light. So they are photo generated in the depletion region and acquires a sufficient energy from the applied electric field to liberate secondary electrons. Got it now? So whatever the free electrons which are applied over here, that is generated by this light, they are liberating secondary electrons and they will liberate tertiary electrons, like that. So it is like a chain-like process and more number of electron and hole pairs are formed. Such type of ionization process is known as impact ionization. Clear now? So the generation of first, second, Third, like this process, a chain-like process within the layer by a process known as impact ionization. This word is very, very important. So how the avalanche breakdown or avalanche multiplication is taking place? By impact ionization. So these newly generated carriers are accelerated by the battery, that is applied electric field, whatever the electric field we are applying. So by this, they are accelerated. So they gain enough energy to cause further impact ionization. Thus, carrier number is increased exponentially, and this effect is known as avalanche effect. Got it now? So photon that enters through this heavily doped p region is absorbed in the intrinsic region, resulting electron hole pair is separated by the electric field in the intrinsic region. So then what is happening? The hole is drifting towards the p and do not take part in the multiplication process. So then what is happening? Now electron is drifting through the intrinsic region to the p-n junction. Okay, such electric field due to this reverse bias is accelerating the electron. So like this, avalanche effect is taking place. Got it now? So now coming to the application part. So here we are not explaining any VI characteristics. Whereas in PIN diode, we have forward and reverse bias. Okay. In the forward bias, it is the current controlled switch. And in the reverse bias, it is acting like a transition capacitance. Whereas in the avalanche photodiode, we don't have any characteristics. Only just we are explaining about what is avalanche photodiode and what principle it is working. Okay. Coming to the construction part and explain about the working. In working, explain clearly by drawing the diagram how the avalanche breakdown or avalanche effect is taking place and how the impact ionization is working. These points you have to mention. Clear now? Coming to the applications, due to the performance advantages of this avalanche photodiodes, they are used for data transmission. That is, in fiber optic communications, I told you already, in the detection part, always we use either PIN or APDs. But in this avalanche effect is more, that is why we always use APDs as a data transmission in optical fiber communication. In range finding also, that is in satellite communications, in LIDARs, photoradars, etc., range finding process also, the optical fiber, that is the APDs are used. And high speed industrial inspection, like including color management, flaws, and defects in order to detect the defects in crystallization, etc. Also, these avalanche photodiodes are used, and distance measurements and in various medical and scientific instruments at a greater level of sensitivity, these are used. Okay, got it now? So these are all applications of PIN photodiode and avalanche photodiode. So with this, we are concluding. So I gave comparisons of PIN and APD also. Got it now? Semiconductor laser. Now the last part is semiconductor laser. Just sir will explain you semiconductor laser in lasers and fiber optics in unit 4. Got it now? Because you should know what is the basic principle of laser. Then only you come across this, what are the principles and how it is working, etc. Because apart from this photodiodes, the working mechanism will be different. But even though, just I'll share you the PPTs also to you. Okay, got it now? So it is semiconductor laser. What is the basic principle? It is nothing but P and N type only. Got it now? So this is all about your unit 3. So I told you these are the short answer questions are definitions of radiative and non-radiative recombinations and differences between LED and PN junction, differences between the PIN and photodiode. Got it now? Yeah, I'll share the topics 2, 3, second and third unit notes also. Please go through it. Okay. And I'll tell you one more thing. In case of this semiconductor, you need not write in detailly the semiconductors. Okay. Always, whenever semiconductor laser question, if you get, you have to write what is a semiconductor laser and what is the classification of semiconductor laser and what is the principle, and write the structure of homojunction, write the structure of heterojunction, and write working same. Got it now? Working principle is same. Energy level band diagram is same. Only thing is the construction part is different. Okay. So remember how it is working. If he is asking heterojunction, draw the heterojunction structure and write working principle. If he is asking homo, write that and write. Got it now? Yes, I'll post you the recording as well as the PDFs of already. I hope in kmitonline.com all 5 unit PDFs are there. If not, I'll post you the PDFs of second and third units also. Okay, all the best. Be prepared. Okay, well prepared.